Chemistry 30, acids and bases. This is lesson 4 for salts, weak bases, and the Kb expression. This goes along with the AB3 assignment. When I add salt to water, the salt will dissolve into the water, producing cations and anions. And if the salt added to the water, if the cations introduced interact with OH minus ions, then it'll cause the OH minus concentration to decrease. And as we know, if the OH minus concentration goes down, the H plus concentration goes up, and the solution will then become acidic. Likewise, if the salt introduced produces anions that partially interact with the H plus ions, that's going to cause the H plus concentration to decrease, which means the OH minus concentration will increase and the solution will become basic. Likewise, the Ka values found on the data table can be converted to Kb through this equation. Ka times Kb equals Kw. As the Ka increases, Kb decreases, and vice versa, but they're always equal to the same number, 1 times 10 to the negative 14. Consider what would happen if NaCN was added to water. NaCN will separate into its ions, Na plus and Cn minus. NaOH is a strong base which fully dissociates, so we know that adding Na plus ions will not affect pH. As we know from solutions in solubility, Na plus does not form a solid with anybody and has no interest in interacting with any of the anions. So it will just float around in solution, minding its own business, and does not affect pH. But HCN is a weak acid. It does not fully dissociate. So we know that if we add Cn minus ions, they will seek out H plus ions, causing the solution to become basic. Those Cn minus ions will interact with the H plus, tying it up, and if the H plus concentration decreases, the OH minus concentration increases. So Cn minus will find a water, it will swipe an H plus from it on occasion, turning itself into HCN and producing a hydroxide ion. Since water is readily available and composed of H plus and OH minus ions, the Cn minus ion will strip the H plus ion from the water, producing free hydroxide ions. Example 1, find the Kb value for the equation where cyanide and water react to produce hydrocyanic acid and hydroxide ion. To find the Kb for this reaction, we must locate the Ka value for cyanide's conjugate acid, which is HCN. So when I look on the green sheet, I find HCN has a Ka value of 4.8 times 10 to the negative 10. Now that's the Ka value for HCN, but we've got Cn minus, which is the conjugate base. So we have to find the Kb value. Now we know that Kb multiplied by Ka equals Kw. So if I'm looking for Kb, I have to isolate Kb by dividing both sides by Ka. Kw is 1 times 10 to the negative 14, and from the green sheet, we know that the Ka value is 4.8 times 10 to the negative 10. We run it through our calculator, and the Kb value for cyanide is 2.1 times 10 to the negative 5. Example 2. Determine the pH of a 0.050 molar NaCN solution. When sodium cyanide is placed in water, it is going to dissociate 100% into sodium ion and cyanide ion. The sodium ion will not interact with anything, but that cyanide ion is the conjugate base of a weak acid, which means cyanide will occasionally want to hook up with an H plus. And where will it get that H plus from? It's going to grab it from a water molecule. And when it does that, it will produce the conjugate acid and hydroxide. This equation is going to be worth marks on the quiz and on the test. So make sure that this equation is written perfectly balanced. All the elements are balanced, but also the charges are balanced. The conjugate base, Cn minus in this case, needs to have the negative charge on it, and the hydroxide needs to have the charge on it. Now I can make my ice chart. Cn minus concentration is 0.050 molar. That's because that's what the concentration of NaCN was. And one NaCN makes one Cn minus. So 0.050 molar NaCN makes 0.050 molar Cn minus. Water, well, it's a liquid, so liquids are eliminated in the equilibrium expression. We're not concerned about it. Make sure that you include that note in your notes. HCN, well, there's none that's naturally occurring inside of the water that this would be added to, and we didn't add any. So we're starting initially with 0 HCN. And the hydroxide concentration, well, we're putting it in distilled water, which has a pH of 7, which means it also has a pOH of 7, which means the OH minus concentration before we begin is 1.00 times 10 to the negative 7, because that is the concentration of hydroxide in neutral water. Now HCN is 0, so that means the right-hand side has to go up because 0 can't go down. And if the right-hand side goes up, the left-hand side has to go down. So at equilibrium, Cn minus will be 0.050 subtract x, HCN will be x, and the hydroxide concentration will be 1 times 10 to the negative 7 plus x. Now with the ice chart made, we'll make our Kb expression, and we will substitute in the values from our equilibrium line in our ice chart, and we're going to take that Kb value from example number 1, where we found the Kb value for Cn minus. First thing I will do is multiply both sides by the denominator, and then I'm going to distribute Kb into the brackets, which will give me this, and I will distribute the x into the brackets on the opposite side, which will give me that. Now I'm going to move all my terms over to either the left side or the right-hand side. I'm going to move everything over to the right-hand side because, as I've said before, I prefer to keep my A value positive. So I'm going to add 2.083 repeating times 10 to the negative 5x to both sides. And I'm going to subtract 1.0416 repeating times 10 to the negative 6 from both sides. And that gives us this here. An A value of 1, a B value of 2.093 repeating times 10 to the negative 5, and a C value of negative 1.0416 repeating times 10 to the negative 6. I write it out in my quadratic without any extra brackets. Once I've done that, I then add in my 3 sets of brackets that I require so that my calculator follows the proper order of operations. So I make sure that I put in extra brackets that will cover the entire numerator, extra set that covers the entire denominator, and an extra set that will encompass everything that should be underneath that square root. Punch it into my calculator. I get an x value of 1.010277 times 10 to the negative 3. So the OH minus concentration at equilibrium is 1.00 times 10 to the negative 7 plus x. So OH minus concentration, we'll add x to 1 times 10 to the negative 7, and that gives us 1.010377 times 10 to the negative 3. I'm going to find the pOH by taking negative log of that concentration, and I get a pOH of 2.9955. We know that pOH plus pH equals 14, so pH will equal 14, subtract that pOH, and that gives us 11.0045, corrected to 2 significant figures, is 11.00. Example 3. Determine the pH of a solution when 48.4 grams of potassium acetate is added to 2.0 liters of water. Now this is a question that is a practical question. We are adding this much salt to this much water. What is the pH going to be? And for that reason, this is what your quiz question is going to look like. This is what your test question is going to look like. I've been given grams. My first step is going to be converting grams to moles. So I'll take 48.4 grams and divide it by the formula weight of potassium acetate. Since I'm looking at equilibrium concentrations, I'm going to want to find the concentration of the potassium acetate, so I will divide it by liters to give me the molarity of potassium acetate. Now, potassium acetate is going to separate into potassium ions and acetate ions. The K plus, I'm not going to have to worry about. We know that KOH is a strong base, thus K plus will not interact with anything we have in solution. But the acetate is a conjugate base of a weak acid. It will, on occasion, hook up with H plus ions. And when it does that, it's going to cause the H plus concentration to decrease. And when the H plus concentration decreases, the OH minus concentration increases, which means the solution will become basic. So the acetate ion will react with water. When it reacts with water, it steals an H plus, turning itself into acetic acid. At the same time, when it steals that H plus from water, it turns water into hydroxide ion. Now on the quiz and on the test, I won't be looking at just the final answer. I will also be looking at this equation to make sure it has been properly balanced, that all the elements are balanced as well as the charge. And from this balanced equation, I will make my ice chart. The initial concentration of acetate is going to be 0.24658. It came from the concentration of potassium acetate we added. H2O is a liquid, so we don't worry about it in our calculations. There initially is no acetic acid present, but since we are adding the salt to distilled water, the hydroxide concentration will be 1.00 times 10 to the negative 7. That is the OH minus concentration of neutral water. Neutral water has a pH of 7, which means the H plus concentration equals the OH minus concentration, and they both equal 1 times 10 to the negative 7. Now in my change line, I have a 0 on the right-hand side. So that means the right-hand side has to be going up. So I put my positive x's on the right-hand side. And if the right-hand side is going up, that means the left-hand side is going down. So I put my negative x's on the left-hand side. So at equilibrium, the acetate ion concentration will be 0.24658 subtract x. Acetic acid concentration will be just x. And the hydroxide concentration will be 1.00 times 10 to the negative 7 plus x. Now to find the Kb value. Well, Kb times Ka equals Kw. So if I want to find Kb, I will divide both sides by Ka to isolate Kb. Kw is always 1 times 10 to the negative 14, and I'm dividing that by 1.8 times 10 to the negative 5. Now, where did that come from? That came from the green sheet. I get it from the Ka value from the green sheet. Now, where do I look on the green sheet? Well, I've got acetate ion. That's my base. So I go down the green sheet and I look for CH3COO-, which I found right here. So the Ka for acetic acid is 1.8 times 10 to the negative 5. So I'm looking for the Kb because I have the acetate ion. I punch that into my calculator. That gives me 5.5 repeating times 10 to the negative 10 as a Kb value. Now make the Kb expression. That's products over reactants. Then we'll substitute in our equilibrium concentrations from our ice chart and the Kb value that we found. I'll multiply both sides by the denominator, then distribute the Kb value into the brackets and the x into the brackets on the other side of the equation. Move all terms over to one side, place into the quadratic, and then solve. Now to find the pH. So we know that the OH minus concentration is 1 times 10 to the negative 7 plus X. So our OH minus equals 1 times 10 to the negative 7 plus X, which then gives us 0.000011754. POH equals negative log of the OH minus, so I will substitute in the hydroxide concentration I have found, and that gives me a POH of 4.93. And we know that POH plus pH equals 14, so pH is equal to 14 subtract that POH, and that gives me a pH of 9.07. And that's the end of the lesson. You're good to work on the AB3 assignment.